I'm sharing over here our last Word file where we didn't get into any of these details. Everything's just typed. This is from an individual practice session of mine going back a couple of months, looking at how the betas in the logistic model are estimated. One thing I wanted to mention was those of you who have experience with Newton-Raphson for approximating a solution to an equation with a single variable, we actually use the multi-dimensional Newton-Raphson. So it's based on all these matrices. Now these betas were for logistic regression. We had a lot of fun with this credit card default dataset with 10,000 borrowers. We're now moving to linear discriminant analysis, where let's just remind each other, this entire chapter is on predicting or making predictions for a variable that takes on qualitative data as opposed to quantitative, as opposed to numerical. Logistic regression, at least in this book, is only used for response variables that are variable. Defaults, does not default, arrives late, does not arrive late, dies within 10 years, does not die within 10 years. For the more general case where you may have a response variable with more than two, we call them classes, we've started looking at Bayes' theorem for classification, where we're using uppercase letter K to represent the number of different classes that may appear for the response variable y. And we kind of switched gears yesterday in terms of the rate at which we were covering or working through this content, slowing down, I would say, considerably, to figure out exactly what's going on in this formula. So going back to my Word file, I think we had typed something, didn't we? Yeah. We'll explain all this notation again. I'll be honest, I could definitely do with a refresher over here as well. But if we just paste this section of the book and just look at this for a second. I'm going to type it out. What we're saying is the following. Bayes' theorem allows us to make the following statement. The probability that y is k, given that x is x, and do remember, x may very well be a vector. So although we're not using bold font, this lowercase x is not necessarily a single real number, but may capture more than a single attribute for each data subject. Well, that probability is the same as, we definitely need to see again what all this notation represents. Pi k, that's some kind of probability. F subscript k of x, that's another probability. And then we're summing over all the different outcomes. And let's see if I know how to type this. No, that wouldn't work. I think I need to do this and this. Okay. So L is just a dummy variable from 1 to uppercase K. So that's just all the possible outcomes. And again, we have pi L FL of X. So we can see why we're definitely taking at least this section a lot slower than maybe our what our speed of learning has been till this point. There's a lot of it's written in a very compact way, but we need to know what the different notation represents. But let's start with pi k. I seem to remember this was simply the probability that y is equal to k. Let's have a look in the book. And pi k represents the overall or prior probability that a randomly chosen observation comes from the kth class. That is, this is the probability that a given observation is associated with the kth category of the response variable y. And yesterday we didn't write it explicitly. Maybe I'll make it slightly clearer what we're saying. We're just saying the probability that y is k. So that's pi, and this is the same thing, but is equal to L. Okay, so that's the first piece of notation. It's the first piece of notation. Now, instead of using the summation, let's make perhaps this more explicit as well. And I'll just type I'm going to delete the summation and we'll just write out the terms individually. So from the first possible class, let's call it K1, to the very last. See if I can shade this entire thing. So plus dot plus all the way till the very last one. So let's just call it uppercase K. Uppercase K. Maybe I'll just call this 1. And we'll just write a short sentence to make it clear. To make it clear. So all that we're saying here is consider response. This is what we're trying to predict. Response variable y with k classes from k equals 1 until k equals uppercase K. The example that the book is taking, or at least one of them, is the patient data set. So it is like the emergency room. 3 classes: stroke, drug overdose, and epileptic. I always get this one wrong. Epileptic seizure. Okay. So over here in that specific example, the one that we just looked at in the book, you would add 3 terms over here. Now what's Bayes' theorem telling us? Bayes' theorem says the following. If you want to know the probability that y is equal to k given X, which, by the way, is what we need from the model. What we would want our model to do in a classification scenario is we would feed it this information. We would feed it this information. So our predictor information, our predictor variables. So imagine a set of symptoms, for instance, 5 of them, 10 of them, 100. And what we need the model to do is actually give us this output. And this would be p hat, right? I'll use green or whatever. Let's not lose sight, and the book very often uses this notation. So please let's not lose sight of the big picture, which I find can easily happen when a lot of notation and algebraic manipulation is going on. It's very, very difficult to keep track of the end goal. Now of course, this would be some kind of estimate, right? So the model does not give us the true probability, but we have, I don't know if you realize, but at no point so far in this chapter, and this is the chapter on classification, have we encountered the error term. Do you remember the error term, epsilon, in chapter 3? So at this point, there has been no reference. I don't know if we're expecting it to appear in a later section. So we give the input data. So you have a patient who's just arrived at the emergency room. You take a set of diagnostics, 10 symptoms, whatever. What you need your model to do is give you the probability. This notation doesn't quite work, does it? This notation was great for, I'm going to have to modify it. This notation, the P of X, was great for the, or was enough for the credit card data set, for the default data set. What was the, why was that fine? Or why was this notation fine for that context? Because that was a binary response variable. So we were taking this notation to represent the probability of default given X. And of course, if you then need the probability that the person does not default, you simply subtract from 1. There are only 2 possible outcomes. If you know the probability of one of those 2, it's very easy to, it's just the complement, right? To calculate the probability of the other outcome. Whereas over here we need to be a bit more specific. So you actually need to write K. K is one of the one of the possible classes. So we said drug overdose. Going back to the emergency room example, drug overdose, epileptic seizure, and what was the other one? Stroke. So K would be stroke, or K would be seizure, or K would be drug overdose. So each time the green notation is telling you the probability of this observation being classified as class K given the X information, which we've already said this once, may very well be a vector. It may consist of more than a single characteristic or predictor variable. Okay. Now, along comes Bayes' theorem, and we'll double check this, but to my knowledge, it tells you, okay, do you need this? Well, you can find it. These kind of swap around, and if this is wrong, we'll 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 soon know because I'll check with the book. But I think this, and let's just write it over here before I type anything else. The book is using this notation. This is simply the probability of x being x given that y is equal to k. Let me just check. I'm not going to share it, but just so we don't lose my drawings. But yeah, the probability that x is x given that y is k, meaning this is replaced with that. Now I'll need to move, but that's okay. This is this, and this is this. Okay, and let's just shift everything back there. And this is what's going on. What we need, if you're interested in a specific class, now of course we would want it for every class, but if you're interested in a specific class, so the probability that the response variable is k given this set of information, then the pink is sort of flipped into, I'll use, what's the color close to pink? Maybe yellow? The pink is flipped into these yellows. We're reversing the order, the conditional order. Instead of the probability of y given x, looking at the probability of x given y. That's Bayes' theorem in a nutshell. We won't do the proof. It's not too difficult from what I remember. But this is Bayes' theorem. Notice that if I use blue, this entire term, the numerator, is always one of the terms in the denominator. It doesn't actually appear over here because of the dots, but it will appear as one of the terms in the denominator. We're not using betas, are we? This is the first time since we started chapter 3, linear regression, where we're looking at a model that isn't estimating beta naught hat, beta 1 hat, up to beta p hat. I'm getting a call. Let me just mute for a second. Sorry about that. Where were we? We're doing, and I am unmuted. We're not estimating any betas. What we're probably going to have to estimate instead, in order to get a working model, is maybe the yellow terms, maybe the yellow values, these. Okay, let's see what the book has to say. In accordance with our earlier notation, we will use the abbreviation pk of x. Can we just emphasize what pk of x is? It's what we discussed earlier. It's what I had typed in green. This is, so we're going to see very often, especially when reading the theory behind this model, we're going to use this notation. I think it's very simple. As with all notation, it does take some time to build familiarity with it, but we're simply saying the probability that the response, so for example, the patient's, so singular, right? Patient, the patient's, the patient's illness is illness K. Given what we know about the patient, maybe their age profile, maybe their symptoms. It's usually, the more data you have, at least you would expect the more confidence you can put in your prediction. So that's the notation. Let's keep it in mind, and let's remind each other what it means. It doesn't appear anywhere over here. You will never see pk over here. Well, for an obvious reason. It's what we're trying to estimate. We're using this to estimate this. Okay? Whereas the other notation is, this is, we were using, I don't think we were using any color, were we? Let me take white. We're going, this is the pi notation. This is pi k, pi 1, pi uppercase K. So that's the overall probability. And this is called the, there's a name for it, but the notation is F subscript K. Be not afraid. Let's encourage each other over here. It's not easy stuff. A few more sessions, we're going to be looking back at this and only praying that the book remains as easy as this content is, in fact. So, in accordance with our earlier notation, we will use the abbreviation P subscript K of X to represent the probability that Y is equal to K given X. This suggests that instead of directly computing pk of X, as in section 4.3.1, so instead of directly computing 4.3.1, this is where we were computing it directly. What do we even mean by directly? Let's have a look. So in the logistic model, it would appear that we were calculating these pk of X probabilities directly, quote unquote. We can simply plug in estimates of pi k and fk of X into 4.10. So we're going to need, as we've been saying, we're going to need estimates of these fk's and estimates of these pi k's. In general, estimating pi k is easy. if we have a random sample of y's from the population. We simply compute the fraction of the training observations that belong to the kth class. So that's very easy. If you want the pi k's, if you want, for example, let's say 1 is seizure. If you want the probability that y equals seizure, just get all your training data set and see from those observations, you might have maybe 100, how many of those 100 observations had as their y seizure. That's very easy to estimate. However, estimating fk of x tends to be more challenging unless we assume some simple forms for these densities. We refer to pk of x as the posterior probability that an observation x equals x belongs to the kth class. That is, it is the probability that the observation belongs to the kth class given the predictor value for that observation. It is the probability. It is the probability given the predictor value. The predictor value? It is the probability. Oh yeah, of course. PK is the posterior. So your Bayes theorem uses two key words: prior and posterior, sort of before and after. Your priors. So kind of think of your priors as your prejudices, what you kind of believe at the outset. Your priors are these. These are your priors. This in the literature, whenever you're making use of Bayes' theorem, this is your posterior probability. So the whites are your priors, pink is posterior. That is, the posterior is the probability. And this is what we want the model to give us, right? The probability that the observation belongs to the kth class given the predictor value for that observation. So once the model is set up, you want it that you want it to be such that you feed it the predictor value for a specific observation. Could be a vector in a more general context, and it gives you the probability that the observation belongs to a specific class. And we were using green, right? Earlier, we had done p hat. So this green, that is p hat k of x. It is this over here. We know from chapter 2 that the Bayes classifier, which classifies an observation to the class for which pk of x is largest, has the lowest possible error rate out of all classifiers. So what we're doing over here, the Bayes classifier, the way it works is you have an observation. And the question is, do you classify it as into class 1, seizure, class 2, epileptic, class 3, overdose, etc., etc. You calculate the probability for each one. You first calculate the probability for each one, calculate the probability, calculate the probability, calculate the probability, and the greatest probability wins. So then if the greatest probability is this middle one, you exclude these two, and this observation would be classified into this bucket, into this class, based on the fact that it was assigned the highest probability, the highest PK. So apparently it has the lowest possible error rate. This is, of course, only true if the terms in 4.10 are all correctly specified. Therefore, if we can find a way to estimate fk of x, then we can develop a classifier that approximates the Bayes classifier. Such an approach is the topic of the following section. So just to take a step back and see what we've covered so far. So in logistic regression, we estimated betas based on the so-called likelihood function, but the book does not go into the specific calculation of maximizing the likelihood function. In fact, we have a note over here that the details of maximum likelihood are beyond the scope of the book. At some point, we could use my own personal notes when I was reading another book on maybe a bit more geared towards actuarial science from its name, but also with heavy emphasis on R. We could actually go into the details, or at least some of the details, of how you would estimate these betas. Really, there are 3 steps. You calculate the log likelihood, which is this over here. Then there's a lot of algebra, and then you solve by using Newton-Raphson. If you've seen Newton-Raphson at A level in the second paper, that was Newton-Raphson when you're solving for a single variable. This is Newton-Raphson in the multi-dimensional case. Now instead, we don't have betas, but we have these fk of x. To think of them as analogous to the betas that we had, I mean, in one way, right? But we need to estimate them, just like we needed to estimate the betas in that sense. And it would appear that unlike the approach the authors took for maximum likelihood, where there's just a note, we're not going to get into this. It might be the case that we are going to get into some of the mathematics behind, and given what we've seen so far in this book, there's probably a very good reason why this might be key to future chapters. So let's have a look. Linear discriminant analysis for p equals 1. Now, universally in this book, p is the number of predictor variables. So it's not the classes. It's not the classes. So you could still have seizure, drug overdose, and stroke. But imagine that you're only looking at a single predictor variable. So the data subjects, the observations, age, for instance. That would be a single predictor variable. For now, assume that p equals 1. That is, we have only one predictor. we would like to obtain an estimate for fk of x that we can plug into for point 10 in order to estimate pk of x. And again and again and again, what is fk of x? It is the probability that x is x. So for example, that the patient's age is 40, given the response variable. So the probability that the observation is age 40 years old, given that they suffered a seizure when they were admitted to the emergency room. In order to estimate fk of x, we shall first make some assumptions about its form. Okay, right. Suppose we assume that fk of x is normal or Gaussian. Now we've been using. Now, don't let this. We'll do it in Desmos in a few minutes time. Just hopefully the term normal is familiar to us. It's what we were using for the error term epsilon in linear regression. It's used in so many different situations where it's doing something else this time around, but it's still the normal distribution. Now, in the one-dimensional setting, the normal density takes this form. And I think it's time to type it into Desmos. So I'll share my screen, press go into Desmos. And let's type it. Yeah, you would think I have it memorized, but it's not actually the case. Okay. So let's have a look. Do you remember that random variables, they have one or more parameters? So for example, it could be the random variable that gives you heads or tails. That's known as a Bernoulli random variable. It just gives you heads or tails. That's a single parameter. For example, 80%, 0.8 would be its parameter. So 80% heads, 20% tails. The normal, we can see it in R very soon as well. The normal distribution, a random variable. A random variable is just something that doesn't always, you're not guaranteed that it gives you the same thing every time. So for example, the heights of individuals, you're not guaranteed that if you pick an individual, if that individual is always going to have, if you take a random individual, take another random individual, they're not always going to have the same height. And that's two parameters. It is mu and sigma. So let's type. I'll type mu. I'll type m for mu. We'll take a mean. That's the mean, by the way. That's 0. And sigma, I'll take s. That is the standard deviation. Kind of it's a measure of the variability within the random variable. We'll take 1 for the time being. And now I can type f of x is equal to 1 over square root of 2 pi s e to the negative 1 on 2 s squared. That's also known as the variance. X minus mu squared, close brackets. And this is the normal distribution. It's the bell curve. In R, you can simulate values from the normal distribution very easily by doing R norm for normal distribution, 100 of them with mean 0 and standard deviation of 1. And we'll call this, for example, data. Let's take 10,000. And we can do histogram. So what I have in Desmos, can I put them maybe side by side? What we have in Desmos over here, the pink. Actually, shall I scale the histogram? Shall I? Is there a way you can frequency? What if I do faults? Yeah, look. You see how it reaches 0.4 over here? The same thing over here. It reaches 0.4. So what it's telling you is, I mean, I'm sure you're all very good at working with histograms, but you know, roughly 40% of the is that how it would work? Yes, right? 40% of the data is between what looks like negative 0.25 and 0. Whereas over here, there's only 10% of the data that's between 1.75 and 2. Do keep track of what the axes are giving you. This is the sort of the probability. And these are the actual data values. So think of heights, think of intelligence, and anything that you would expect would follow this so-called normal distribution. So this is a histogram in R. You're bucketing the data. You're saying, okay, how many values do I have between -2 and -1.75? Between -1.75 and -1.5. So this is a histogram. You can think of this as sort of, I don't know if you ever heard of the word empirical. Empirical is just, you know, hard evidence. Whereas in Desmos, this is the theoretical. We've generated now in practice, and I am sharing the right thing. I hope you should be seeing R and Desmos side by side. In practice, the process would be in this direction. You collect your data, and then you fit a distribution to it. So you would say, my data suggests that whatever I'm measuring people's salaries, you name it. How many pets people keep at home follows this specific theoretical distribution. Why do we like a theoretical distribution? Because normally, mathematically, they're a lot simpler to work with. So you go from your raw data to a more theoretical, algebraically defined description of reality. So you have your raw data description and the theoretical description. What I've done, of course, is I've worked exactly backwards. I've assumed that we have a specific distribution, and I've generated 10,000 values following this distribution. So this is what the book is going to take for the FK. We're assuming a normal distribution. Let me just share Desmos. Now, of course, the shape will depend on these two parameters. This can never be less than 0. The smaller the variability, the more concentrated the data is going to be about a single point. So the smaller your standard deviation is, so for example, take this one for instance. Over here, if your standard deviation is quote unquote only 0.01 and my mean is say 3, then nearly all your data is within 0.05 plus or minus 0.05 of 3. And in a way, this is what we like, right? In real life, well, I mean, it depends on the context, but imagine you're an insurance company. As an insurance company, you could only dream that each car crash follows this kind of distribution where it's you have a high it's you know, financially, let's say we're working in thousands, that you know that most of the car crashes are going to be, or at least, you know, like 95% of them are going to be between 2,950 euros and 3,050 euros. Now, the larger that variability is, that standard deviation is, the more uncertainty there is. The data is more spread out. Okay. Now, let's see. So this is just an assumption. So it's not a question of why, it's just an assumption. Our assumption is that we're going to work with an FK, which is normally, or also known as Gaussian, distributed. In the one-dimensional setting, this is the algebraic description of the probability density function. Think of it as the histogram of this normally distributed FK, where mu k is the mean and sigma k is the standard deviation. When you square it, then you have the variance parameters for the kth class. For now, let us further assume that each class, seizure, drug overdose, stroke, have the same variance. It's just a simplification. That is, there is a shared variance term across all k classes, which for simplicity we can denote by sigma squared. A similar situation in chapter 3 linear regression, where we were taking the error term for each observation to also have each observation had the same error term with the same variance. Plugging 4.11 into 4.10, we now get this formula. Meaning now to estimate this, to estimate the probability that an observation is in class K given a specific characteristic, for example, age. Now all we need to know is sigma, and for each class, mu k. If you know all the mu's, or all the means, you know all the sigmas, then you can calculate this formula. You can compute this expression, you can evaluate it. Note that in 4.12, pi k denotes the prior probability that an observation belongs to the kth class, not to be confused with the ratio of the circumference to the diameter. The Bayes classifier involves assigning an observation x equals k to the class for which 4.12 is largest. Taking the log of 4.12, so taking the log of all this and rearranging the terms, it is not hard to show that this is equivalent to assigning the observation to the class for which this is largest. Don't ask me how they got this. We are running out of time, but it might be something worth doing at some point, where we could actually take logs. So if you had to take logs, I mean, you know, you'd have to do subtraction. I think the summation becomes multiplication, right? When you take logs, log x plus log y is log xy. But anyway, if you do all of that, apparently, the largest, the class K seizure, drug overdose, the class K with the largest PK will be the one for which this is largest. So if you calculate this expression for every k, and every observation x, you shall classify x. You shall classify the observation into class K, into that class that gives you the largest pink value. For instance, if k equals 2 and the probability of class 1 is the same as the probability of class 2, so 50% and 50%, right? Then the Bayes classifier assigns an observation to class 1 if if it satisfies this inequality. We'll have to see these details later on. I mean later on, maybe in tomorrow's session. I wonder. They're probably just it's probably very simple. Probably very simple algebra. Yeah, it's probably just very simple algebra. Definitely not to be done in the last few minutes of a session. In this case, the Bayes decision boundary corresponds to the point where, okay, so this is this is going to be like some kind of cutoff point. An example is shown in the left-hand panel of figure 4.4. So figure 4.4, the left, let's see. Two one-dimensional normal density functions are shown. So one for each class. We know what classes are, right? You're going to classify each observation into a specific class. And we're assuming that we have two classes. The green class and the pink class. They have the same variance. Do you see they have the same variance? They have the same variance, but they have different means. Does this mean? And does this mean? The dashed vertical line, apparently in this situation, is just the mean of the means. It is the mean of the means, right? Mean 1 plus mean 2, division by 2, the mean of the means. So this is the theoretical picture. Whereas over here, this is what's actually going on. And look, it does a pretty good job, right? It's the black, the solid line is the model's estimate. The true decision boundary. What do we mean by decision boundary? That it's classifying anything to the left as green. And it's classifying everything to the right as pink. It does get some of them wrong, right? So for example, we have an observation, which is roughly it's would it be the x? Yeah, it would be the predictor variable. We have an observation. We have one observation with an x of like roughly, negative 1.75. It's incorrectly classified as green. Green could be seizure, for instance. These greens are incorrectly classified as pink. But it's getting most of them correct. We're drawing a line. That's kind of like a cutoff point. Anything to the left will be classified as green. Anything to the right will be classified as pink. So I actually think we'll definitely go over these ideas again when we next meet. But next to yesterday, I'm feeling more confident that we should be able to make good progress. It really gets interesting, and we'll finish on this point. It really gets interesting when you have more than a single predictor variable, because instead of working with what we had in Desmos, which were probability density curves, you know, like the histogram that we had in R. Instead, you're going to get these density surfaces. So, you know, whenever you're working, the technical word is multivariate. You're taking, and I promise you, this is the last thing that I'll say. You're taking this, but instead of a curve, it's now going to be a surface or higher dimensional object. And we'll stop over here.